Let's talk about this word problem first. We'll pray for the volleyball team, football game tonight. And anybody else? Prayer requests? Yes, Emily?
Well, my family's house really
Relatives or?
It's my grandparents.
Sorry to hear that. Okay, pray for Emily's grandparents. Will? Spoken. Peyton? And Kendall?
No, Will.
Who?
No, Will. He says grandma's funeral.
And Jesus, we love you. Ask you, Lord, please bless our day. Please be with John Will Piper, Lord, and help him and his family through this time. Please be with Emily's grandparents as they seek to recover from loss due to the storm. Ask you for unspoken requests. Ask you for the football game tonight, Lord. Bless the students with safety and no injuries. Be with the volleyball team as they travel. Give them safe travel mercies both directions. Help them be a light representing you and our school, Lord, and help them also to have victory. Ask you, Lord, please bless our time together today in Jesus' name. Amen. Okay, let's work this problem together. Cool, brand new mark. What are we looking for here? Gloria, what's the first thing I write?
T with the subscript of F, like equals question mark in Kelvin.
Kelvin, okay. Now, one thing to make sure, be sure this is a capital K. If it's not a capital K, it's going to be confused with the kilo that we're going to have later on in the problem, okay? So big K is always Kelvin. Small k represents kilometers or kilojoules or kilo whatever. Okay, so what do we know? We're going to write down our other T, our V's. We got three things we need to know here, V1, T1, and T1. I call them ones and twos. You can call them initial and final. Either way works. The initial temperature is given as 10 degrees Celsius. I'd get rid of that right away since it says we have to do this in Kelvin. On your little cards, it tells you how to convert that. Most of you might know already. Just add 273. Okay, at the bottom of your card, of your conversion factors, it says Celsius plus 273 equals Kelvin. So this becomes what? 283. Okay, so just do it right away. Get rid of it. You won't have to memorize or remember later on. Initial velocity, the volume is 1.4. No, it's not. 3.6. And this is the small k, okay? Small k for kilo, big K for Kelvin. And the V2 here goes to 1.4. I got this all messed up. 1.4 kiloliters. And how do I write deca?
Small D. Big D.
Yeah, you can't just use a small d because that's deci. Remember in your King Henry acrostic, we've got two D's. So one of them's not a D. I got King Henry died by drinking chocolate milk. Unfortunately, two D's means one of them can't stay just a D because nobody would ever know, am I talking about something 10 times the base or something that's 10 times smaller than the base? So we always use DA, as Olivia said, for deca. Okay, so decaliters is going to be small d, small a, capital L. This is why I never gave this one back to you. Okay, there's a few tricky things on this one here that some of you didn't know. So decaliters, kiloliters, Kelvin, and we're ready to go. Okay, write the formula down. It's given to you. Whoops, goes up. This is Charles's law, which governs hot air balloons. When the balloon heats up, its volume gets bigger. When it gets bigger, its density gets less. When the density is less than that of air, the balloon goes up. When the temperature of the air inside the balloon cools down, its density gets denser. It becomes denser than air, and then it starts to sink. So it's a buoyancy thing. What makes a hot air balloon go up and down is simply buoyancy. Is it less dense or greater than the air around it?
So like when the hot air balloon's going up and it's like filling up, it's like all the oxygen going out and then when we pull it down, it's coming back in.
Yeah, so on a hot air balloon, if you've ever seen them, the bottom is not sealed. So yes, as it heats up, it can suck a little bit of extra air in, but really the air that's inside the balloon basically expands. And when it expands, it doesn't really get that much bigger, a little bit bigger, but the density goes down. So hot air is less dense than cold air, which is why hot air rises in your house. If you have a 2-story house, your second story is always going to be warmer because the heat from the first floor is going to rise to the second floor. In a smoke-filled room, you always crawl along the floor because it's cooler, but also there's less smoke down there. But the air down here is always cooler than the air up here. So if you want to stay cool on a hot summer day, lay on the floor. No, I thought that was because the floor was cold. Yeah, but also the air down there is cooler as well. Okay, solve this for T2, or T final, as Gloria said. Okay, you can do this a number of different ways. The easiest way is to cross multiply and then divide by the variable you don't want. If I cross multiply, I end up with V1 T2 equals V2 T1. Remember, I got to get this thing out of the denominator. I can't leave it in the denominator and solve this. So the easiest way is to cross multiply and then divide by what we don't want. So getting rid of the T1, and with V2 equals V1 T2 over T1. I did it. Yep, I did it wrong. Thank you. T2, divide by V1 to get rid of that. There we go. Okay, T2 equals, there we go, T1 V2 over V1. Okay, now we're ready to substitute. $283 Kelvin times the initial one, 3.8. Wait. Yeah, it's 1.4 milliliters, 3.6 hectoliters. Good. Substitute in. I got my final volume first in the numerator, according to my equation, and my initial volume here. I need to do one thing to reconcile these two sizes. There's two different sizes here. So I need to know how many deciliters are in 1 kiloliter, small k. So I go over here, and it's really easy because we go King, Henry, died. Oh, there's my deca. So how many decas in a kilo? 100. And we're done. Ready to get the calculator out. 283 times 1.4 times 100 divided by 3.6. Make sure all my units cancel out. And we get. Do something.
11,006.
Yeah, let's round it off to 2 decimal places here. Let's call it 11,000 Kelvin. So what's going to happen to our balloon? It'll catch on fire. Okay? There's nothing in the world that I know of that can withstand 11,000 Kelvin without burning, okay, or melting, even if it's a metal balloon. So this is a really cool problem, but unfortunately it's not realistic, because 11,000 Kelvin is 10,780 Celsius, which is about 20,000 Fahrenheit. So yeah. But anyways, that's where we get. Now, could you, I had somebody ask, can we change these to liters right up here and then substitute them after? You can, but if you show me your work, okay, change deciliters to liters, it's going to take you 2 steps, whereas over there it only took 1 step. But I think in the wash it's about the same. If you like doing it here, we put deciliters down here and liters here, so there's 10 deciliters, 10 liters in a deciliter, and down here we change our kiloliters to liters, and there's 1,000 liters in a kiloliter. So I'm going to change both these to liters so they cancel out over here. Which one's more work, which one's less work, you know. As long as you show me what you're doing here, you can do it here. But in this case, I know I can do this in 1 step, deca to kilo, and so you know, just do 1 calculation here instead of 2 calculations over there. Questions? Good. Okay, put that away. Let's take a look at chapter 5. We're going to dig into our lesson on orbitals. Okay, yesterday we watched the short video about Schrodinger's work, and I love that video. Again, if anybody wants the link here, you can get it from me, send me an email, and I'll send it to you, or you can just Google on YouTube, Schrodinger's, I'm not sure what the title of it was. We'll watch it again sometime next week, but if you want to watch it a couple times, it does a really good job of explaining what in the world these orbitals look like, and how come they represent a probability. So let's talk about that for a little bit before we get into some details. Now this picture here, you don't need to memorize, okay? I put this up here because I want you to realize there is a whole world beyond chemistry that deals with quantum physics or quantum mechanics. And quantum mechanics deals with the newest branch of physics, which deals with how do we reconcile the incredibly tall rules of nature with the incredibly big rules of nature. We call it Einstein's equations and Newton's equations. How do we reconcile this with the tiny things that go on inside an atom? Because so far, they seem to follow two different set of rules. Scientists seem to think there's one set of rules that govern everything in the universe, and so they've come up with a couple different theories. One's called quantum mechanics, and this leads to a discussion of something called string theory. Now, I'm just throwing this out there. I'm not going to test you on it, but if anybody's interested, there's some really cool stuff in the last 10 years dealing with string theory. It's a branch of physics. It has nothing to do with strings, but it has everything to do with this. Waves and particles acting like each other. Okay? And you can sort of see, if you draw these wavelengths in circles, they sort of look like strings, like jump ropes is how I picture them. And there's some good videos on YouTube if anybody's interested in Googling some of this stuff, where you can see some really cool computer simulations of what these things might look like if we could see them on a microscopic scale, smaller than an atom. But again, Bohr's work and then de Broglie's work led to this equation right here. So we left off here yesterday. Just jot this one down. I want to point out one thing about this equation. You don't need to memorize it, and as far as I know, I'm not going to test you with any questions that deal with this equation, but I want you to know the significance of this equation. This equation shows the relationship between mass, right here, and wavelength, right here. De Broglie came up with this equation, still using Planck's constant, so going back to Max Planck's work, and m times v is actually momentum. I don't know if you remember that from last year, but momentum, conservation of momentum, is m times v. And so that equation is significant because de Broglie said, hey, I can show the relationship between mass of a particle and a wavelength. Again, the photon equation is sort of built into this. Everybody see the E equals hv in there, right? Different v, but h times nu was our photon equation. So I want you to be aware of the significance of this. For the first time, we have an equation that shows the relationship between mass and wavelength, between a particle and a wave. Right with me? Now, don't forget, the other two equations from this chapter you do need to know. You need to know the C equals lambda nu 1. We've done, that's a nu, not a oo. And then you do need to know the energy one, okay, equals h times nu. So these two I want you to know and know how to use them. You've done some homework problems with them, which eventually we will go over. I'm sorry I haven't gotten around to it yet. But this one, I just want you aware of it. I want you to know the significance of it. And it is de Broglie's equation. Let's call it that, okay? Okay. Heisenberg's our next guy, and just to mention something that he's known for, and it's related to what we've already talked about. It's the fact that Heisenberg's uncertainty principle. He said, you know what, we cannot know two things about an electron. We can know how fast it's going, or where it is, but not both. And there's a mathematical reason for that, which is beyond us, okay? But we can either know where it is or how fast it's moving, but not both. It's like the pictures I showed you in chapter 4 of the race car. I can take a very fast shutter speed picture of a race car and I know exactly where it is, but not how fast it's moving. Or I can slow down the shutter speed and get a blur. If I get a blurry picture, what can I do? I can calculate how fast it's moving, but I have no idea of knowing where in that blur it is. Okay, so this is the race car picture that I showed you when we talked about wave-particle duality in chapter 4. It's called officially the Heisenberg uncertainty principle. Okay. Heisenberg's uncertainty principle led to this probability. Okay, and this is where Schrodinger picked up on the work. Okay, we can't know where it is, we can't know how fast it's moving, we can't know both of those, but I can write a big old equation that tells me the probability that it is somewhere. So let's say, what is the probability that Will Perry on Thursday at noon is to be found? Okay, we could write it great. We might say there's a 97% probability he'll be in the cafeteria on Thursday at 12 o'clock. There's probably a 1% or 2% chance that he's in the restroom in the old high school building at 12 o'clock on Thursday. It might be 0.5% probability he's in the restroom in the new wing because he really had to go and he trailed behind everybody else. And there might be 0.5% probability that he's out sick that day because he's never out sick. Okay? And so that's what the probability just says, where is he likely to be found? We've got a 97% probability he's in one spot. That's all these equations that Schrodinger and these guys came up with, saying there's a percent probability that these electrons are in this region. Which table is he sitting at? Don't know. Which chair is he sitting at? Don't know. Which stall in the bathroom is he in? Don't know, don't want to know, okay? But there's a percent probability he is in this particular location. Got it? Okay, ignore that one. And so Schrodinger picks up the work, he does the math, and he comes up with what we call the quantum mechanical model of the atom. You and I refer to it as the electron cloud. It's the same. The official title. Schrodinger's equation, that big old one you saw in the video yesterday, applies not just to hydrogen. Whose work only applied to hydrogen? Bohr, okay? So Bohr was limited because his work only applied to that one electron of hydrogen, but Schrodinger's much more complex equations applied to all atoms. Okay, so this wave function that Schrodinger gave us predicts a three-dimensional region around the atom where we will find an electron. Okay, and those predicted regions are called orbitals. And we'll spend the next half hour talking about orbitals. I need the last one again. Quantum mechanical model, other elements in hydrogen, and that leads to orbitals. Now take a look at the picture here. Now the picture we saw yesterday on the board with the video showed a different shape than this. This is a picture of an orbital that would be spherical in shape. And again, it's not showing 1,000 different electrons. If I could take a picture of a single electron 1,000 times in a row, this would be a picture of the 1,000 places it might show up. yesterday on the video, we saw that there was a different shape, a different kind of orbital that sort of looked like this. And he said something like this, and he had a donut shape in the middle, and another thing down here. And he said, if I take this one electron and shoot it 10,000 times, take a picture of it 10,000 times, there's a picture that starts to appear with all these dots, right? And that shows the probability that that electron is in those regions. Same thing here. What's the probability that electron shows up in this region? And this is just a dot diagram, if you don't call it that, but it's just showing me a density map, I guess is what they call it, of where the electron could be. Okay, so Schrodinger's wave functions predict a probability map or probability location for electrons. Okay, let's stop here for now. I'm going to get off the slides here for a second and jump over to the board. First thing I want to talk about is the periodic table. Now, chapter 6 is going to be our chapter on the periodic table. Unfortunately, we haven't covered it yet. So let's talk about it for a second. Periodic table consists of the picture you see on the wall. Most of you have seen it before. It's in the back cover of your book as well. Okay, we have 18 columns. Each of those is called a group. And there's some definite differences. We got the left-hand side, which sort of sticks up, and then we got this empty space in the middle, and then we got this chunk over here. And I have cut off helium, okay, for a very specific reason. And then we have the ones that always appear at the bottom of the table, okay? Now, one thing I want to point out before I start this is that these two rows, over there they go up and down. Your book puts them at the bottom. They actually fit into the periodic table here, okay? They actually fit right between here. So the actual periodic table goes like this, and then this piece is way over here on the right-hand side. But because it's so long, publishers of books cut it out and stick it on the bottom, okay? And it drives us chemists crazy, but that's where it goes. Everybody understand? Houston, you understand? Okay. Now there's a name for each of these blocks. I cut mine into 4 pieces for a very specific reason. And they're going to relate to orbitals. Where'd you go? Okay, so let's draw this out here. Here, on the left-hand side, the first 2 columns, first 2 groups of periodic table is called the S block. I'm going to put a small s in it. All of the orbitals represented by those elements in its outermost level are going to be S-type orbitals. Just write it down. It'll make more sense. I'm going to give them a name. I'm going to tell you the shape. And we'll start to load some electrons into these things so you can know how elements get their electrons. Okay? Now, the next thing in the periodic table is that really flat part at the bottom. And then we got a block here. And then over here, we got a block as well. Okay, each one of these I call a block. You got the small ones on the left called the S block. And you got the 6 on the right. Everybody see up there on the right-hand side, if I cut helium off, I got a block 6 wide, right? And that's called the P block. So put a small p in here. The third block I want you to notice is right in the middle of our main periodic table here. We call these transition metals or transition elements. They go from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, all the way down to the bottom. And this is your D block. D. And it is 10 elements wide, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The P block is 6 elements wide, 1, 2, 3, 4, 5, 6. The S block is 2 elements wide. And the last one, again, which fits in the middle, right here, is called your F block. Your F orbitals. And it is 14 elements wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, well, you know, something like that. 14 elements wide. So the names of the orbitals are S, P, D, and F. That's the order you want to memorize them in. S, P, D, and F. I don't have a fancy way of memorizing that. Spud. Okay? But S, P, D, and F. If you think of it, S, P, D, F. Now, what do those letters mean? Okay? They don't mean anything. The letters themselves don't. They represent a different shape for each of the types of orbitals represented. All of our S orbitals are going to look like this, a sphere. Okay? S orbitals are spherical. That's easy to remember. This picture on the board behind me represents the probability that an electron is in an S orbital is spherical. Real simple. Okay, so if I have hydrogen way up here with one electron, okay, then it's going to be a spherical shape. That electron is thought to be rotating in a spherical shape. Again, at any point in time, it could be anywhere. It's moving almost the speed of light. So we would see something that looks like this. Now, how about a helium? Say, Mr. Dempsey, where did helium disappear to? You cut it off the top of the P block. And that's because the helium, the second electron added, which is helium's electron, doesn't go up here. Sorry to say. It goes here, right next to the hydrogen. Okay? So we put helium, when we're talking about orbitals, helium actually goes right here. And you'll find some that helium and hydrogen are the exceptions to the rule. Sometimes helium acts like it should go over there, and sometimes later in the year I'm going to tell you that hydrogen acts like it should go way over on the right-hand side of the periodic table, okay? And it acts like a halogen. So these two are special, but for our discussion in Chapter 5 about orbitals, helium goes right there. And it's going to have two electrons. Instead of one electron, it's going to have two electrons in this spherical orbital. We would draw it as a sphere. You and I, on two-dimensional paper, need to draw it as a circle. And if it's hydrogen, we call it energy level 1, S orbital, 1 electron. That's all that means. If it's helium, I've got energy level 1, it's an S orbital, and it's got 2 electrons in it. Now, what does the energy level mean? Remember what Mr. Bohr came up with. He came up with the fact that there are different energy levels. And I told you that they correspond to the families, or not the families, the periods on the periodic table. So each row, hydrogen and helium are the only two in the first row. So those are the only two that only have electrons in their first energy level. The minute I get to the second row, lithium, all the way over to neon, I have a second energy level. From sodium all the way over to argon, I have a third energy level. From potassium all the way to krypton, I have a fourth energy level, and so on. There's only 7 possible energy levels. I should say only, which there's less, okay? So, hydrogen, 1 electron, helium, 2 electrons. Then I'm going to number 3. Number 3 on the periodic table is lithium. Lithium is in the second row down, so it has a second energy level. Now, one of the rules that you read about last night is that no orbital can hold more than 2 electrons. So this orbital is now full once I get to helium. So where does lithium's third electron go? It needs to add another S orbital. This one's going to be a little bit bigger because it's got more energy. We might draw it a little bit bigger. It's going to look, again, like a sphere. In the middle is some infant, 10,000 times smaller than that circle, is the nucleus with all the protons and neutrons. But lithium is going to have 1 electron in a spherical orbital, and it's going to have 2 electrons in a smaller spherical orbital inside. Okay, so it's got kind of like what Bohr thought, a ring inside of a ring. And that's going to be energy level 2. s orbital with 1 electron. That's lithium. So lithium's got 3 electrons. It's got 2 electrons in its first energy level, s orbital, and it's got 1 electron in its second energy level, s orbital. 2 orbitals, one bigger than the other. What happens when I get to beryllium? Beryllium has 4 electrons. Well, this one can hold another electron. It's like a maximum holding capacity of a orbital is 2. Okay? So I can hold the second one. We're going to put that one right there. So we can call that 2s2. This is beryllium. 2 electrons in its first shell, first orbital. 2 electrons in its second energy level, first orbital. Now, when something happens when we go to boron, boron up there on the periodic table is number 5. So we've got to find a home for a 5th electron. But it's not in energy level 3. So I can't add a 3rd one of these and make it even bigger until I get to sodium. So what do I do with boron? Boron's going to add a new type of orbital. So this is called our p orbital over here, our p block. And p orbitals are completely different than s orbitals. They have a different shape. There's 3 of them instead of 1 of them, and they have different orientations. Okay, so let me draw you a p orbital. P orbitals look like, tell you what, let's do this. P orbitals look like this, and they're similar to the one you saw in the video. Let me switch to black. P orbitals are sort of shaped like the ones we saw in the video yesterday. They have 2 lobes, but these don't have that donut shape in the middle, okay? So again, what does this represent? This is a probability that that electron for boron is going to be either here or here. Do we know where it is? No, not exactly. It's in one of these 2 areas. Where's the nucleus? The nucleus is right there, but it's so tiny we can't see it. Okay, so boron picks up its 5th electron. It has 2 here, it has 2 here, and then it has the 5th electron. I'm going to pick a spot and put it there, just for the sake of a picture. And this is our first p orbital. It's in energy level 2, so we're going to write 2p, and it's got 1 electron. Boom, 2p1. Okay, let's keep going. Let's look at carbon. Carbon is the next element over. Carbon has 6 electrons. It has 2 in its first energy level, s orbital. It has 2 electrons in its second energy level, s orbital. It has 1 electron in its first 2p orbital. And now something funny happens, okay? And again, you read about this last night, and I'm trying to explain it. We'll get to it over the course of the next couple days. But there's something called Hund's rule, which means every kid gets his own bedroom until we don't have enough rooms. Watch. I'll explain in a second. I don't put a second electron here yet. The second electron is going to go in a p orbital, which still looks like this. We call it a dumbbell shape, because it looks like it's got 2 sides and we can do curls with it. Okay? This one goes up and down, this one goes side to side. We call them x and y axes. And we're going to stick 1 electron there. That's the carbon. Carbon has now added an electron to a new p orbital. This is a different p orbital, and it's got 1 electron in it. One of them goes up and down, one goes side to side. So this one's zipping back and forth here at the speed of light. This one's zipping back and forth here at the speed of light. They never bump into each other. It's amazing. Now we get to nitrogen. Nitrogen has 7 electrons. 2 in its first energy level s orbital, 2 in its second energy level first orbital, 1 in its first p orbital, 1 in its second p orbital, and 1 in the third p orbital, which looks the same shape, but instead of going up and down or side to side, it's sticking out of the board at you. Okay? It's the z-axis. It's hard for me to draw this, so I'm going to put it at an angle. But picture this one is going into the wall and sticking out of the wall. X, Y, and Z. You know, I can pick this X, Y, and Z. Got 3 dimensions. Those of you who've done some CAD work with engineering or with Mr. Freud know that in the SolidWorks or Solid Edge programs, we have this little thing in the middle, X, Y, and Z. Shows 3 dimensions. So this one's sticking out. Nitrogen's going to put electron somewhere in here. Again, it's a probability. It's a mathematical equation that says somewhere in this region, there's our 7th electron. Now, when I get to oxygen, now we can start pairing them up. Okay? Oxygen has 8 electrons. I'm still in the 2nd energy level. I can't add any more p orbitals because there's only a maximum of 3 p orbitals in any energy level. So now, where did that come from? Now, oxygen's going to add a second electron to its first p orbital. Okay, so I'm going to have 2 because the maximum contained in each orbital is 2. Now let me tell you why this happens. It's like this. Suppose you're married and you have 3 kids. And you go buy a nice house, and your house has 4 bedrooms. Okay? So mom and dad share a bedroom, typically. And if you have 4 bedrooms and 3 kids, each kid gets their own bedroom, right? Okay. What happens when mom and dad have baby number 4? Okay? Now, they don't want to move to a new house, or they don't want to put the kid in this stairwell like my wife and I did years ago. And the baby crib in the stairwell. Okay? But so now you go and buy what? Bunk beds. And you start building bunk beds in the first bedroom because baby number 4 is going in with one of the other kids. So this is the bunk bed that we've now added, okay? And electron number 4 in my p orbitals has to go somewhere, so we're going to start bunking them up. Okay? Baby 5 comes. And what do? We add a bunk bed to the 2nd bedroom, okay? And baby number 6 comes. Oh boy, okay? We never had, yeah, we lost. And baby number 6 comes along and gets added to the 3rd set of bunk beds. So now I have 3 bedrooms with 2 kids in each, or 3 orbitals with 2 electrons max each. Never try and do more because it won't happen. And I have 6 electrons. What do those correspond to? 6 groups. 1, 2, 3, 4, 5, 6. Okay? Each pair of electrons represents an orbital. Okay? We finished energy level 2. So I've got a total of 2p6 electrons all the way over here, and I'm up to neon. 2p2, 2p4, 2p6. I'm all the way up to 6 electrons in my 2nd energy level p orbitals. We're going to go down to the next element, number 11, sodium. Now we got some problems. Okay, what does sodium do? Well, sodium's way over on the left, so it's not a p orbital, it's a s orbital. What's the shape of an s orbital? Sphere. Okay, so now I got a 3rd, energy level 3 starts with a bigger sphere. More energy, farther away from the nucleus, and it's going to have 1 electron if it's sodium, and it's going to have 2 electrons if it's magnesium. It's an s orbital, it's an energy level 3, and I'm going to go sodium 1, magnesium 2. Now think about this with me, guys. This is actually what's going on. Inside of magnesium, we have 2 electrons in a sphere, small sphere. Then we have 2 electrons in a bigger sphere. And then I have 6 electrons in this crazy XYZ thing. 2 here, 2 here, 2 here. They're all in there as well. And then on top of that, I'm adding a 3rd energy level with 2 more electrons. All of these are on top of each other. If I could take some of those transparencies, which I might try and do, I'm not sure, I'm not an artist, but if I could take some of those transparencies and draw each one of these things on a second transparency and lay them on top of each other, you'd start to get the idea of what's going on inside the atom. And it's crazy. It's insanely crazy. And Schrodinger figured it all out with that math that you saw yesterday. It's like, whoa, okay? And he did like 5 screens worth of math in 3 seconds just to show. That was just for hydrogen. Yeah, right. Okay, so these all lay on top of each other. What happens when I get to aluminum? Ready? Aluminum is now in the p block. We're back over here. P orbitals are shaped like this, but they have more energy than the second level. So my 3p orbitals are going to be further away and a little bit bigger. Can't do that. Ooh. Somebody yell at me if I try and do that, okay? Okay. Blue. So let's make them a little bit bigger and a little bit further away. So aluminum adds 1 electron into this orbital. Is it right on top of it? No, they kind of, he said yesterday, they push each other away because electrons repel electrons. But it's going to be in the same region, sort of, but not quite. Okay, and then we're going to go to silicon. Silicon adds another electron. Bigger, further away. And then we're going to go to phosphorus, which adds another electron in this region. P orbitals, energy level 3, further away. So now I've got, and then I start pairing them up. And then I got sulfur, second electron, and chlorine, second electron, and argon, second electron. So we're up to 18. I got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Everyone's accounted for. Everybody's got a place to stay. Okay, everybody's got a bed to sleep in. Okay, what happens, Mr. Debsky, when we go to potassium? Number 19. Tell me, somebody tell me, what happens when I go to potassium? Potassium. Symbol K, number 19. Michael? Sorry. Michael? Olivia? And get another sphere. Okay, we got 4th energy level, s orbital, big boy, okay? Get up here. 4th energy level, s orbital with 1 electron for potassium. Calcium in your bones, add a second electron. We're up to 20 electrons. Okay? Scandium, 21 electrons. Whoa, what happens now, Mr. Dempsey? That's not S and that's not P. You're right. We're now in D. F's down here. We don't get there for a few more rows. Okay? So we're now in D. Scandium right here is the first of our D orbitals. Do D orbitals look like this? No. Do D orbitals look like this? No. Take your textbook out, please. Turn to page 154, figure 5.17. Now, this shows you the s orbitals and the p orbitals. And it shows you an artist's rendition of what the d orbitals kind of look like. At this point in high school chemistry, teachers don't have you memorize these, okay? You need to know S's are spherical and P's are dumbbell shaped. When we ask you d orbitals, you say, yep, there's 5 of them, and they got some really weird shapes. And that's what I need you to know, okay? Because they start entering 2-dimensional lobes. And if you look at the 5th one there, that's the one he drew on the board yesterday with the donut shape in the middle and the 2 lobes at top. I don't even know how to explain that in words, okay? What you need to know is that the D shapes are different. There's 5 of them. Who in the world knows what x squared minus y squared axis is? I'm not sure, okay? 5 of them, each holding 2 electrons, giving me a total of 10. And that's why if you look at the middle part of the periodic table here, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. 10 elements wide. We're adding 1 more electron to each of those weird shapes. Good? So I'm not going to try and draw it. I can't. I mean, my math skills are good, but my drawing skills are not up to that. And once we start laying these all on top of each other, you can see there's a cloud of electrons going on here, okay? And it really gets complex. Now, the natural question is, what do F orbitals look like? Anybody want to know?
Yeah.
Your textbook doesn't even give you a picture, okay? Most textbooks at this level, unless you start taking some advanced physics classes in college, don't even include pictures of F orbitals. But you're welcome to Google them, like this, and see some of the crazy shapes, okay? And they might look something like this. This one's pretty good. Some of them look like a double ring pop. That's what I call that one, okay? Some of them have 6 lobes, 1, 2, 3, 4, 5, 6. So the first electron would go into the blues, and the second electron would go into the reds. Okay? This one has 6 lobes. This one has 8 lobes. This one has 8 lobes. This one has 6 lobes go in that direction instead of that direction or that direction. And this one has 6 lobes go in that direction instead of that. I mean, it's just crazy complicated. What you need to know is that there's 7 of them, 7 different shapes. 1, 2, 3, 4, 5, 6, 7. Each one can hold 2 electrons for a maximum of 14. If you ever forget, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 elements in the F block. Really easy to remember. I'm showing you this kind of out of sequence of the book because the periodic table gives you some big hints. S orbitals, there's only one of them, because there's only 2 elements in the S block. P orbitals, there's 3 of them, because there's 6 elements each orbital can hold 2. D block, you can count 10 wide. 5 orbitals, 2 electrons each. F orbitals, 7 of them, 2 electrons apiece, 14 wide. So this is a really cool tool. You can cut out your own periodic table. When we get to chapter 6, I'll give you a picture of the periodic table. You're going to have some fun with it, but then you can eventually cut it apart if you want and do this kind of thing with it. So the F orbitals, don't worry about it. I'll never ask you about it, okay? So let's go back here for a second. What would I do? Say we're talking about scandium, SC, it's got 21 electrons. We can write out where those electrons are this way. It's got 2 electrons in its energy level 1, S orbital, 2 electrons. Hydrogen, helium. Then lithium or beryllium. We've got 2 more electrons, energy level 2. S orbital, 2 electrons. Boron, carbon, nitrogen, oxygen, fluorine, neon. That's my P block. It's still in energy level 2, second row of the periodic table. Total of 6 electrons. We're not up to scandium yet, so now I'm in the 3rd energy level, sodium and magnesium. S. Level 3, S orbital, 2 electrons. Aluminum, silicon, phosphorus, sulfur, chlorine, argon. P block, 6 electrons. I'm still not at scandium yet, so we go down to the 4th row. Calcium and potassium. Energy level 4, S block, 2 electrons. And then scandium has 1 more electron. Here's where the pattern stops, and I'll have to explain it to you next week. It goes into the 3D1. Now it's a d orbital because it's in the d block. It's got 1 electron, that's all it's got in the d block. The reason that this is a 3 is because what science has shown is that the energy associated with the d in row 3 goes with the elements that are actually in row 4. Exactly. Now, there's a rule next week. I'll show you on that. Okay, and the F's do something like that too. Okay? So from here, we go 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10, and then we go back to 4P. Because we're in the 4th row. And we start adding the next 6 electrons for gallium, germanium, arsenic, selenium, bromine, krypton. But this is a good place to stop for today. And questions? We have 3 3 minutes. That's the beginning. That's the beginning. Okay. Okay, the takeaway today, number one, know the shapes. You should know. S orbitals are spherical, P orbitals are dumbbell shaped, and the D and F ones are crazy. Okay? Number two, how many S orbitals are there per energy level? Only one. How many P orbitals are there per energy level? 3. 3 times 2 is 6. How many D orbitals are there per energy level? 5. 5 times 2 is 10. How many F orbitals are there per energy level? 7. Okay, so it goes 1, 3, 5, 7. Listen, the numbers are 1, 3, 5, and 7. The first 4 odd numbers. Okay? And I didn't design that, God did. And I think that's really cool. 1, 3, 5, 7 times 2 gives us the exact number of electrons in S, P, D, and F orbitals. It's just a masterpiece, if you ask me. So I am amazed at how God designed this thing. You have, I forgot to put the homework on board. Hang on a second. Sorry about that. I got it. I think you got 3 days to work on it, so you can work on that for you. I will.
So I really don't have
I didn't say that. Depends if you think I can.
You're a pretty funny guy, so.
that. Yeah.
I'm what?
You're a pretty funny guy, so I think you can see.
I'm so jealous.
34 through 66.
Wait, look at the videos.
I'm gonna scroll into Tuesday, and that is not gonna be done.
Bragging, Mr. Coward? Are you bragging that you're not going to be going?
Please just check his.
Hillary.
Well, it looks like you need the points.
What?
Grade's close today.
Well, start off good for next year, buddy. We need to get into orbitals.
Actually, I need to have it done by 3 o'clock on Monday.
I literally have never laughed so hard.
You don't think we're going to finish this chapter?
It's like a lawnmower.
I was like, I'm 46, I'm 40, I'm 41, and then
Was he recording?
No, I still got the video back. That's for the volleyball players, so.
You want that,
Make sure you tell him